Hi mathematicians, we are moving right along into section 2.6 and we're going to talk about continuity, which is also an important theme when we're talking about derivatives and integrals, anything that has to do with calculus. You're often also talking about continuity. And so the really informal definition the really easy check is if you can draw the function without picking up your pen it is continuous. Okay, it doesn't have breaks. No breaks, no holes. Okay, that's the informal definition. That's our intuitive notion of what it means to be continuous or not. So if I were to draw a function here, okay, this is clearly continuous. I did not pick up my pen. There are no breaks, there are no holes. But if I were to draw something like this, this is not continuous, right? There's breaks, there's holes. All right, so that's what we're talking about. And first, when we're talking about continuity, we're first going to talk about continuity at a point. And so a function f is continuous at a point A if the limit as x approaches a of f of x equals the f of a. Okay, and so in order for this to be true, a couple other things need to be true that are kind of embedded in this whole thing. Three different aspects of this on our checklist. First of all, f of a needs to exist. It's defined. Okay? That means that f of a can't be something over 0. Right? Second thing that needs to happen is this limit needs to exist. And so then the third thing, of course, is that they equal each other. Okay? All right, so let's go ahead and do some examples. So example 1 in your book. I guess I'm going to go ahead and show the book now. Zoom in on this graph they want me to talk about. Okay, and so they're saying, given this figure here, identify values of x on the interval 0 to 7, so where they showed us, right? They want us to identify points of discontinuity. So we're looking for points where things aren't defined, the limit of something does not equal the output somewhere, things of that accord. Okay, and so as we go along in our interval, right, first of all, f is 0, and we're looking at the interval 0 to 7, so I guess we're not actually looking at 0, but if we were, right, f of 0 is not defined here. F of 0 is not defined. right? Likewise, f of 1 is not defined. So it's not continuous here either, right? Not continuous, not continuous. F of 2 is defined, but it does not equal the limit, right? The limit here is going to be 1, right? The limit is f of x as x goes to 2 is 1, clearly. Because as we approach 2 from the right-hand side and the left-hand side, we're getting closer and closer to this 1. However, our f of 2 is up here, is 3. So that our f of a, in other words, doesn't equal our limit. So that's a problem. That's a place of discontinuity. At x equals 3, another place of discontinuity, right? There is no limit here. As you approach from the right-hand side, it does not equal the approach from the left-hand side. And clearly we have a jump. Okay. At 5, we're not continuous at 5. Why? Because we're not even defined at 5. Right? Our f of 5 does not exist. F of 5 does not exist. Okay, so let me write, I'm actually going to move this over. And I talked a lot, but I didn't write a lot of things down. And so here we're going to go through and we're going to list all, I'm going to call them discontinuities. Okay, and I'm going to write y. So f of 0 does not exist or is not defined. Okay, f of 1 again is not defined. F of 2, right, so here was our f of 0, not defined, there's a hole there. F of 1, not defined, there's a hole there. F of 2, I can see this break, right? So f of 2 equals 3, but the limit as x approaches 2 equals 1. They're both defined, but they don't equal each other. So since the f of 2 does not equal the limit of x approaches 2 of f of x, right? Therefore, we have, this is a break. What else? Okay, our f of 5 is not defined. And then my f of 7 is also not defined. F of 7. Okay, technically they asked us to look at 0, 7, which does not include 0 or 7. So we technically didn't have to do those ones, but I just couldn't help myself. Let's go ahead. I'm going to do example 2 now. So this is example 2. Determine whether the following functions are continuous at A. Justify your answer. Okay. So we have f of x equals 3x squared plus 2x plus 1 over x minus 1. And we're looking at a equals 1. Okay, and so we're asking, is this continuous at a equals 1? And so we want to look at, is f of a defined? Is the limit of f of x as x approaches a defined? And then lastly, if they are both defined, do they equal each other? Those are the three things that we're checking, right? 1, 2, 3. So is f of a defined? I put 1 in there. What do I get? Right? I get 3 plus 2. I get 6 over 0. Not defined. Therefore, the function, I'm just going to say f of x, is not continuous at A. Okay? Let's do another one. We have g of x equals 3x squared plus 2x plus 1 over x minus 1 for a equals 2. And again, we're checking three things. We're checking, is f of a defined? We're checking the limit of f of x as x approaches a. See if that's defined. And then lastly, we're going to check to see if they're equal. And so, first of all, is f of a defined? I know f of 2, pardon me, I should put f of 1 up there. I know that f of 2 is going to equal 3 times 2 squared plus 2 times 2 plus 1 over 2 minus 1. We're going to have no problems here, right? We're going to have 4, 12 plus 4, 16, 17. Is this 17 over 1? There's no one here to check my math. I think so. It looks okay. I hope so. Yell at me at home, I guess, if it's not right. Okay, now let's look at the limit. So let's look at the limit of 3x squared plus 2x plus 1 as x goes to 2. X minus 1. Okay, we're just going to go ahead and plug this in. It's not going to cause any problems, and guess what? We're going to end up with the same thing. And so because our f of 2 equals our limit as x approaches 2 of g of x, or it was a g. These should all be g's. G of g of x. Therefore, g of x is continuous at 2. Okay? All right, let's do one more, and then I'll shut down this video. And so we're going to look at h of x equals x sine 1 over x if x doesn't equal 0, and 0 if x does equal 0, and that's for a equal to 0. Okay, so we want to look at the h of a. We want to look at the limit as x approaches a of h of x, and we want to see, are they the same? Okay, those are 3 questions. So first, let's go ahead h of 0 equals, if x equals 0, our h of a, or if x equals 0, our h of 0 is going to equal 0 here. So our output is 0. Now let's look at the limit as x approaches 0, right? Our a is 0, that's where I got it over here. And so we want to look from the left-hand side and from the right-hand side. And so what's happening here? So we're going to have sine of 1 over, let's go from the right. Okay, and so what do we have here? I am going to go ahead and I'm going to use the squeeze theorem here, actually. So I'm not going to look from the left and the right. I'm just going to go ahead and say that I know that sine of 1x is always less than or equal to 1 and negative 1, right? I know it's between these two. And I know that x is always, x sine 1 over x, is always going to be less than or equal to x, but greater than or equal to negative x. And so why would I know that? Right? I know obviously x is less than or equal to x, and x is greater than or equal to negative x. That's for sure. And I know sine is either going to be 1 or negative 1. So all that this is going to do is change the sign, make it smaller, right? So this is definitely true. Well, the limit as x approaches 0 of negative x is 0, and the limit as x approaches 0 of x equals 0. So therefore, the limit of x sine 1 over x as x approaches 0 equals 0. So this equals 0, this equals 0. Are they equal? Yes. So therefore, h of x is continuous at a equals 0. Okay?